This video is a review of derivatives and differentiability. First thing we'll talk about is what you're actually doing when you're taking a derivative. So when you take a derivative, you're finding the value of the slope of the line tangent to the curve at a given point, or you're finding an expression for the slope of the tangent line at any point. So this would end up being version 2 of this limit definition, and this would end up being version 1. But basically what we're finding is some way to determine what the slope of the tangent line to a curve is at some value. Derivatives have certain notation that we've seen before: f prime of x, d dx, dy dx, or y prime. Those are the most common derivative notations you'll see. And then we have version 1 and version 2 of the limit definition of the derivative. This one that's written in red, the limit as h approaches 0 of f of x plus h minus f of x all over h, is the definition of the derivative that you'll see for a general derivative. So that's something that would work every time. The green one only works at a specific point. So at the point where x equals c is where the limit as x approaches c of f of x minus f of c over x minus c ends up working out. So number 4 says use one of these versions of the limit definition of the derivative to find f prime of 2 given what f of x is. I've already written out using the limit definition of the derivative in general. So you take f of x plus h minus f of x over h and take the limit of that as h approaches 0, and you do some algebra. Everything will cancel out that doesn't have an h in it in the numerator, otherwise you did it wrong. Then you can factor out an h and cancel all the h's, and then you substitute h in. That's version 1. I'm now going to do version 2 just to show us what's happening. So version 2 would be the limit as x approaches 2, because I'm finding the value at 2 of x squared minus 2. That's f of x. And then minus f of c. So what is f of c? So the function value at 2 would be 4 minus 2, which is 2, all over x minus c, which is x minus 2. So then I take limit as x approaches 2 of x squared minus 4 over x minus 2. I could factor the numerator into x plus 2, x minus 2. These x minus 2's would cancel, and I'm left with x plus 2. I substitute 2 in, and I get 4, which is, of course, the same answer that I had before. One thing I want to point out about this is that x plus 2 is not the derivative. So it's important to understand that if you use version 2, you're not going to get an expression for the derivative. You're only going to get the value of the derivative at that one point. So the value of the derivative is 4, but this expression is not the actual derivative. Whereas if you use version 1, what you'll end up doing is you end up getting an actual expression that will work every time. So if I wanted to find f prime of 4, I could use this expression, substitute 4 in, and get the value. 4 different instances where differentiability fails to exist: a corner, cusp, vertical tangent, and discontinuity. And I have examples of those 4 here. Essentially, corners are where you have the derivative from one side not equaling the derivative on the other side and their numerical values. Cusps are where you have the derivative from one side and the derivative from the other side being different kinds of infinities. So it ends up being similar to a corner, but it's a little curvy. Vertical tangents are where the derivative is infinity at a point, and then it goes off to something else. So the tangent line ends up being vertical at that point. And then any discontinuity also gives you something that is not differentiable. So for example, y equals 1 over x, you have a vertical asymptote. This function, which ends up having a hole, or any other type of discontinuity, a jump or something like that. Remember that differentiability implies continuity. So if a function is differentiable, it must be continuous at that point. If you have something that's discontinuous, that automatically means it's not differentiable at whatever point there is a discontinuity. Now we're going to match functions on the left with the derivative on the right. So the derivative is, remember, the slope of the tangent line. So if I look at these functions, number 1 has negative tangent line slopes that are getting steeper and steeper until you get to 3, where the tangent line ends up going toward negative infinity. So if we look at all of these over here, we have all of my slopes. Remember, this is the graph of the derivative. If we look at letter E, all of the slopes are negative, and they're getting increasingly more negative until we get toward negative 3, where it goes off toward negative infinity. So 1 is E. 2, we have negative slopes that get increasingly steeper as we approach some sort of discontinuity at 1, and then we have positive slopes that are getting increasingly or decreasing in terms of their positivity. So if we look at all of the derivative graphs, we have all these negative slope values or negative derivatives, and all of these positive derivative values, no value at the asymptote, and it ends up getting really close to 0 as you go off toward the infinities, which is kind of what's happening with these slopes too. So that's C. If we look at number 3, I'm going to have horizontal tangent lines at 0 and 2. Horizontal tangent lines have derivative 0. If I look at graph A, those derivatives are 0 at 0 and 2. Then if I look at the slopes, I have positive slopes before 0, negative slopes between 0 and 2, and positive slopes everywhere after 2. Positive slopes up here, and then negative numbers representing negative slopes because the derivative represents what the slope is all of the time. So 3 is A. Number 4, I have positive slopes everywhere that are leveling off. So it starts at a very positive high number and then increasingly levels off. It's starting somewhere around negative 3. So if I look at this graph, I have positive slopes that are increasingly leveling off as I go on forever. So that's going to be B, and that leaves this one to be D. I have slopes that are low, and then they start getting high. Slopes are low down here, start getting high. This is going to be the function e to the x, which has the exact same derivative as its original function. Lastly, determine if each function below is differentiable at the given point. So in order to do that, we need to remember the definition of differentiability. A function is differentiable, 1, if the function is continuous at the value c, whatever point c it is. So in part A, it's going to be Number 6 it'll be 2, and number 7 it'll be 0. And so let's remember what continuity is. It means the limit from the left is equal to the limit from the right, which is equal to the value of the function. Then also, in order for the function, so the function has to be continuous, but then also we have to notice that the limit as x approaches that value of the derivative from the left has to equal the limit as x approaches that value from the right of the derivative. So both of those things have to be true. Essentially, the function has to be continuous, and then the derivative has to be continuous. So we have to have both of those things be true. So if I look at number 6 and I substitute in 2 to my function, I see that the function value is 5. The limit as x approaches 2 from the left of the function is definitely going to be 5 because it's going to be the same. Then the value of the function's limit from the right, if I plug in 2, I get 8 minus 3, which is also 5. So the function is continuous. Then I have to look at the derivative. So if I look at the derivative is 2x, and I know I'm using shortcuts here, but the derivative is 2x from the left and 4 from the right. If I plug in 2, I get 4 from the left and the right. And I'm not going to use limit notation just to save time, but all of them are going to work, so the derivative is 4 in this spot. Therefore, the function is differentiable at the value x equals 2. Now we're going to look at number 7. If I take the derivative, it's 2 minus, well, it's 2 minus x, kind of. We have to understand what absolute value means. Absolute value is actually a piecewise function where when x is greater than or equal to 0, you get x, but when x is less than 0, you get negative x. So what I'm actually going to do is I'm going to rewrite this function as the piecewise function so then I can see it a little clearer. So 2x minus x plus 1, or 2x plus x plus 1, depending on when x is positive or negative. So I'm going to rewrite this top one as x plus 1. I'm going to rewrite this bottom one as 3x plus 1. Now I know the function's continuous because if I substitute in 0, I get 1 from both sides. So the function is continuous. But the question is the function differentiable? So if I take the derivative of this function, I get 1 when x is greater than or greater than 0. But x, the derivative is 3 when x is less than 0. Because that's the case, since these two aren't the same, f prime of 0 does not exist. There is no derivative of this function at 0. There's derivatives everywhere else, but not at 0.